Let's look at these build your understanding problems. I hope they went okay for you. First, we'll convert the exponential equation t equals 8 to the x into a logarithmic equation. So the equivalent logarithmic equation says that the logarithm on base 8 that you would need, in other words, the exponent you'd need on base 8 to get answer t, that exponent is x. Then we'll convert a logarithmic equation, log base 3 of x equals 5, to an exponential equation. So this is saying the base on the exponent is 3. Remember, the log is always equal to the exponent. And then the thing right after the log and base is the answer you would get using that base and that exponent. Okay, so feel free to let me know if you had trouble with that. Let's go on and talk about graphs of logarithmic functions. We'll graph the function f of x equals log base 2 of x. Now, there's a couple of tricks for doing this. Trick number 1 is to get rid of the function notation and just call it y equals log base 2 of x. And the reason I want to do that is because of trick number 2, which is to not work with the logarithmic equation. Why? Because it's too difficult. When you're thinking about logarithms, it's like you're thinking of something kind of inside out, and it's hard to know what's going on. So the trick here is to convert that to the exponential equation that's equivalent. So I'm going to say x is the answer I get when I raise 2 to the exponent y. And then I guess there's one more trick here. We're going to make an xy table putting numbers in for y, not x. So usually when you make an xy table, you think of putting numbers in for x and computing y. And that doesn't work very well here because y is a logarithm, and it's hard to know what a logarithm is. So instead, we're going to put in numbers for y, and we'll use the formula that the x we get for each y will be 2 to the y. So for example, if y is 3, say, x would be 2 cubed, which is 8. That's not hard to do if you do it in that order. Let's use 2, 1, 0, -1, -2. So when y is 2, x would be 2 squared, which is 4. When y is 1, x would be 2 to the first power, which is 2. When y is 0, x would be 2 to the 0 power, which is 1. When y is 1, x would be 2 to the negative first power, which is 1/2. And when y is -2, x will be 2 to the -2 power, which is 1/4. So let's plot those. So I have the point 8, 3. Let's see, I need to put some coordinates in on here. We'll have each mark represent 1 unit. Like that. Okay, and then we have 8, 3. So 8, 3 is a dot on our graph. And then we have 4, 2. Then we have 2, 1. 1, 0. 1/2 -1. And 1/4 -2. Let's also put in one more line on our xy table. What if y was -3? Then x would be 2 to the -3 power, which is 1/8. So we have the point 1/8 -3. So what's going to happen is smaller and smaller x's are going to be corresponding to bigger negative values of y. So our graph will look something like that. Okay, so this is our graph of f of x equals log base 2 of x. Now that we have a visual of what a log function would look like, let's notice some properties. F of x is always increasing. That is, it's always going uphill. But notice it levels off. So it keeps going up, but it goes up more slowly. Maybe the best way to say this is it starts out very steep, then increases slower and slower. So it's always increasing, it's always going uphill, but it slows down its rate of increase as it goes along. What else? Let's see. It's going through 1, 0. In other words, its x-intercept is at x equals 1. By the way, these properties are not just for the log base 2 graph, they work for all log graphs. And you might wonder, well, why would they all go through 1, 0? That came from this line here, that calculation there, where the x that we computed was 2 to the 0, but it wouldn't matter what the base was. You're always going to get a 1 if you put in a 0 for y. Let's see, what else can we say? Well, to the left of 1, 0, in other words, when x is less than 1, the y values are negative. To the right of 1, 0, in other words, when x is greater than 1, the y values are positive. The y-axis is a vertical asymptote. More negative y values. So going down this way, if you let your y values go down through the negative numbers, you keep getting smaller and smaller fractions for your x value, which squishes the graph up against the y-axis. And one reason that's important to know, besides the vertical asymptote business, is that the domain is all x's greater than 0. In other words, from 0 to infinity, not including 0. Because that graph never touches the y-axis, where x is equal to 0, and it never goes to the left of the y-axis, where x is negative. So the takeaway from that is you cannot do logarithm of a negative number That just does not exist. There's no such thing. And you cannot do the logarithm of 0. That does not exist. There's just no such thing. You only can do log of a positive greater than 0 number. That's the stuff that's okay. Before we go on to the next video, please do the Build Your Understanding problem on the next page, where I ask you to use the 3 tricks from the example we just did to graph the function f of x equals log base 3 of x. And I've got a hint there for you. So the 3 tricks were first to change the f of x to a y, and then switch to the exponential version of this, and then put in numbers for y, not for x. So and in the hint, I'm suggesting you use 2, 1, 0, -1, and -2. So use those to get the x values, then plot the points, connect the dots, and please compare your graph to the graph we did in example 3. It should look pretty similar, and it should exhibit the same properties that we observed in example 3. Okay, good luck with that. I'll go over this with you at the beginning of the next video.